Thermal expansion sample problem 3. In previous video, chapter 4, uh, thermal expansion example 2, we study the uh, aluminum, stainless steel. Here we do have a additional material which is a copper and is a chemical element and shown by Cu. It's a soft, malleable, and ductile metal, very high thermal and electrical, has a very high thermal and electrical conductivity. Main use of that in engineering is used as a strain gauge, and definitely there are different usage of copper in industry. Let's go back to our example. In this example, we see a two solid cylindrical shaft consists of a one of them copper, the other is aluminum, different lengths, mhm, but the same diameters, mhm, and there is a small opening between the two material. When temperature is T1 is equal to 60 degree Fahrenheit. We want to see if we want to close the gap, what is the temperature needed to expand the both material to barely close the gap. So the, that's T2 we are looking for. That's the first part. And the second part, it says if T2 or maybe T3 this time goes by increase to 300 degree Fahrenheit from 60 degree, what would be the average normal stresses in both materials? Let's attempt the first part to see what is the needed temperature to barely close the gap, the opening, and then proceed to solve the second part. In this kind of problem, the very first part is just going to table of material properties within textbook to see what is your specification for different material. For example, for aluminum, elasticity modulus is 10 to 10 cube ksi. Uh, Alpha stands for coefficient of thermal expansion. Sigma y is a yield stress for aluminum, which is 40 ksi. Likewise, for copper, we do have modulus of elasticity, which is a bit higher than the aluminum, coefficient of thermal expansion, and yield stress for copper. The question is asking what is the needed temperature, what temperature is needed to barely close the gap. If we want to know what would be the temperature to barely close the gap between the two material, the gap opening of 0.01 inches. To attempt this problem, to see what is the temperature to make that happen, we can write down the equation for deformation delta due to temperature, which includes addition both materials, both of them, addition of aluminum which and copper. So that's alpha delta TL for both materials. And if you replace that from what we just learned, the delta T should close the opening of 0.01. That's the meaning of barely close the gap, and just replace the numeric value, and T2 is our unknown. If you solve this equation, it gives you a temperature of 112 degrees Fahrenheit is needed to just close the gap between the materials. And as that's for the first part. And the second part, it says when the temperature rises to 300, so we know when we increase the temperature from 60 degrees to 112, already the gap is closed. After that, any increase in temperature just pushes the material to each other. So there is a contact force between them. So from part B, it's exactly like the thermal expansion example 2, which you can find that in, I will provide you with the link for that video as well in the description of uh, mm, this this video. So as soon as the gap close, extra thermal expansion creates a force which we call that contact force, which is again applies to both materials, and that's the same force because that's the contact force. Due to compatibility again, now this time 0.01 inches, which is delta T, should goes by a increase in temperature. Just assume we are increasing from 60 degrees to 300. So again, opening is at the beginning of the problem, we do have the opening, gradually increasing the temperature from 60 to 300. That should close the gap and increase the develop the contact force as well. So that's due to delta temperature, positive delta temperature for copper, positive delta temperature for aluminum, minus contact force. As you can see, it pushes both material as copper as well as aluminum, minus delta F for aluminum. Mhm. And if you write the numeric value for that, again, the opening, the 0.01 opening, it's a positive in temperature for first material minus push, which is unknown, plus a positive in temperature effect, 300 minus 60, 300 minus 60, which is T2 minus T1, and again force which is unknown times length of the second material over denominator is EA. If you do so, the only unknown of this problem is force, which gives you a force equal to 31.37 kilopounds. As soon as you know the force, dividing force by cross-sectional area gives you the stresses in both material, because the force is the same due to the same contact force, and also we do know the cross-sectional area of both material are the same due to problem statement. So sigma is F over A. If F is the same, sigma area is the same, sigma remains the same. So sigma aluminum is equal to sigma copper, and that's nothing but force over area, force 31.37 kilopounds over pi over 4, a quarter of pi times 1.25 square inches. Mhm. It gives you 25.57 KSI, which stands for kilopounds square inches, the unit of stress. And let's check our solution. Since sigma aluminum, which we calculate, is 25.57, which is smaller than sigma yield of aluminum from problem statement, and likewise sigma Cu of the problem calculation, which is 25, again 0.57, and smaller than yield stress of copper. The